So hopefully, I think we're live. So welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host today. Today, we're very happy presenting regularization of self-fields in the gravitational two-body problem by Francisco Blanco. Francisco is currently a Max Planck Fellow at the Albert Einstein Institute in Germany. He completed his bachelor degree in physics at University of Buenos Aires, or Universidad de Buenos Aires in Argentina, and his PhD in 2025 at Cornell University in the US. He's an expert on foundations of the two-body problem in general relativity, perturbation theory, and the self-force. And today we will hear about a regularization scheme for the self-force, which I believe it's valid at any order in perturbation theory, but we'll see what Francisco has to say. So remember that you can ask questions over email or through our YouTube channel, and then the questions will be read at the end of the talk. So without further ado, we will turn it over to Francisco. And Francisco, thanks for joining us today.
Thank you so much for the invitation. It's a pleasure to be here. Does the slide work okay?
Perfect. Yeah, we can see
Amazing.
it pretty well.
Okay. So yes, I'm going to be talking about self-fields in the two-body problem, and specifically in the self-force. This is some work that I've been doing with Abe Hart in Dublin City University and Aina Flanagan, my former PhD advisor at Cornell University. And because this talk is about gravity, I thought I would start with sharing the first time I saw the Einstein equations in a trip to Uyuni, Bolivia. And I was in high school, so I didn't understand what I was seeing, but I was captivated by the symbols. And because this is a Latin American seminar, I thought I should say that. The first time I saw them was in Bolivia. So the outline of the presentation goes something like this. I will start giving an overview of the two-body problem in GR. What are the typical sources, the experiments, and the methods we have to studying these gravitational wave emitting systems. Then I'm going to get into the self-force theory specifically. On the top of the slide, hopefully you can see the different sections and how many slides there are. So GSF is gravitational self-force. Then I'm going to get into the actual idea that I'm going to be presenting, which is a way to deal with self-gravitating objects and how to describe them as test objects. So how to take the self-field and put it into some regularization of the mass or the energy and effectively describe them as test objects. And the last two sections are some quick applications to extended bodies and tidal effects and things like that. And then lastly, how to describe the conservative sector of the dynamics, because the systems radiate. So there is a piece that is dissipative and a piece that is conservative. And the conservative sector can be described with a Hamiltonian. So I'm going to be talking about that a bit. So let's start with the two-body problem. We have a gravitationally bound two-body system. The systems have different masses, different spins. The objects have masses between 1 to 10 solar masses, like a neutron star or a small black hole, up to 10 to the 6 solar masses, which would be a supermassive black hole. They can be spinning around in different axes. The orbits can be complex and eccentric, and these are the primary sources of gravitational waves. We have detected gravitational waves, as you probably know, with LIGO. The frequency sensitivity of LIGO is between 10 Hertz and 10 to the 4 Hertz. And because the frequency of a gravitational wave is inversely proportional to the mass of the system, LIGO is best suited for comparable mass in spirals. So two neutron stars, a neutron star and a black hole, two black holes of stellar mass. But in the future, we are going to have LISA and other experiments as well. Hopefully, it will launch in 10 years. And because LISA is going to be floating in space, it doesn't have any earthly noise. There's no seismic noise. So the frequency sensitivity is much lower, and that allows to detect much more massive systems, like comparable mass in spirals of supermassive black holes, and also the system that I'm going to be mostly interested in, which is extreme mass ratio in spirals of one small stellar mass object into a supermassive black hole. So let me say a few things about MRIs, extreme mass ratio in spirals. So MRIs are a mess, as you can see in the picture. There's a primary object that has mass m and a secondary with a smaller mass mu. And the main characteristic of these systems is that there's a separation of scales. There's an orbital timescale, and then there's a much, much slower radiation reaction timescale. And you can think of it in the following way. If you completely neglected the field of the secondary, it would just move in a geodesic and it would never radiate. So the radiation reaction timescale would be infinite. So because we're including the small field of secondary, the radiation timescale scales like 1 over the mass ratio. So it's very long and inversely proportional to the mass of the secondary. And this means that the system is going to go over 10 to the 5, 10 to the 6 cycles before merging. And these orbits can be eccentric and complicated, and they can get really close to the strong gravity region of the primary. So these are really, really good probes of the strong gravity regime of general relativity. So now taking a step back and seeing the whole two-body problem, there's many different approximations that one can use to study this. So here, let me explain the plot. The axis going from left to right is whether the binary system is very close or very far away. The axis going down and up is whether the orbit is bound. It would be elliptical in the Newtonian case, or if it's a scattering event, so hyperbolic in the Newtonian case. And then the axis going into the screen is the mass ratio. So if the masses are comparable or if it's an asymmetric binary system. And each of these corners is best suited for a different type of approximation. The post-Newtonian approximation expands in powers of 1 over the speed of light. In dimensionless magnitudes, it would be the velocity of the system over the speed of light. And because of the Virial theorem, that means that it describes systems that are very far away. And of course, the zeroth order is just Newtonian gravity. For eccentric systems, we have post-Minkowskian theories that in this approximation, we expand in powers of g. So setting g to 0, we have special relativity. So the objects just go and don't see each other, and they pass each other in straight lines. And as we add powers of g, this approximation is much more related to Feynman diagrams, amplitudes, particle physics, quantum field theory, because people tend to use diagrammatics and have the two particles exchanging gravitons and producing the scattering event in that way. Numerical relativity works best when all the scales of the system are similar. So the two objects are close, they have similar masses, and so on. And it starts to fail if the system is very widely separated or if the masses are very different, because it starts accumulating a lot of error after each orbit. For the case of asymmetric masses, we use the self-force formalism that expands in powers of the mass ratio. And like I said, the zeroth order is just geodesic motion. So it has the virtue that it's already full GR in the zeroth order. So in some way, it's already including strong gravity effects, even at zeroth order, as opposed to the post-Newtonian or post-Minkowskian approximations that are missing some aspect of GR. Okay, so with that, let's get into a self-force. Like I said, the zeroth order of the self-force approximation is just geodesic motion. So let's talk a bit about that. When we have a test body in general relativity, a test body is an object that is not back reacting on the spacetime, so it's not producing its own gravitational field. These objects move along geodesics of the external geometry. And the two conditions are it's weakly self-gravitating, so it's a test object, we can ignore its self-field, and it has to be sufficiently small so it doesn't, the form and tidal effects and extended body effects don't affect its motion. But of course, the question is, how do we incorporate the object's self-gravity? And this is the central question of the self-force program. Let me give a naive explanation of what are the main obstacles in the self-force. So we know that the mass ratio is small. I'm going to call it epsilon. So we want to expand the metric tensor and the stress energy tensor in powers of epsilon, and we want to plug them into the Einstein equations. On the left of the Einstein equations is the Einstein tensor, which has all the curvature, and the right-hand side is the stress energy tensor that is sourced by some matter degrees of freedom m. So expanding in powers of epsilon, we get a series of equations in a perturbative expansion. Equation 4 is fine. It's telling us that the background geometry is a vacuum solution. So if the primary object is some black hole, then G0 is the metric of that black hole. Equation 5 tells us that the first order metric perturbation is sourced by the first order stress energy tensor. That's fine. And the last equation, equation 6, is where we start to have big problems, because the last term in the right-hand side of equation 6 is telling us that the first order field H1 squared is going to enter as a source for H2. And that is a problem in the point particle limit, which is eventually the limit that we always want to take, because we don't care about the fluid dynamics of a neutron star. We want to have the basic point particle plus quadrupole, but not an extended object. And the problem is very simple to understand. This term scales like 2 factors of h and 2 derivatives. And because we're doing a point particle limit, the self field of the object is going to scale like 1 over r. There's the Newtonian potential or Coulomb piece of the potential. And this is 1 over r to the fourth, which is too divergent to be integrated as a source. So immediately in the point particle limit, the second order equations don't make sense, which is it's obvious if you think about it, because point particles are ill-defined in general relativity. If you take a point particle and you put it in GR, it collapses into a black hole. It's not a stable thing that you can just use as an object. And this is exactly that. As soon as we turned on nonlinearities at second order, the point particle limit breaks down. But there's an even more basic problem that already arises at first order, and it's plaguing the whole perturbative expansion. And it goes something like this. Schematically, this is the gravitational field that we care about. The gray piece is the primary that is sourcing some central gravitational well, and the red piece is whatever correction is coming from the secondary. That is a much smaller object orbiting around the primary. Now, we are setting up the perturbative expansion as if the field of the secondary is a small correction over the primary, which is true in most places of spacetime, but it's absolutely not true close to the secondary, because it's divergent close to the secondary. And the problem is that that's precisely where we want to evaluate the field, because the self-force is the interaction between the secondary and its own field, which is divergent at its own position. So we are expanding as if the metric perturbation h is small, but we need to evaluate it at the position of the secondary, where it's not small at all, it's actually divergent. So the whole perturbative expansion doesn't really make sense. So how does the self-force fix this problem? The idea is that the secondary object is not going to move in the full geometry. It's not going to move in this spacetime. It's going to move in some properly regularized effective metric, where we somehow transformed the physical full metric by subtracting the singular piece of the secondary. So somehow there's a method to take this red 1 over r piece and take it out so that only a regular piece remains, which produces a self-force via the interaction with the secondary. And this approach can be done with a lot of hard work up to second order in the gravitational self-force. This is work that Adam Pound and Lear Barak do in Southampton, Barry Wardell in Dublin, Martin van der Mint in Copenhagen, and many more people work on this. And it basically requires, one way or another, to take a world tube around the secondary and take it out of the spacetime and replace it by some smooth continuation of the boundary conditions in such a way that you get rid of the singularity. But there's a lot of problems with this approach. So far, people struggle to calculate it in different gauges. Sometimes there's a loss of covariance because you need to specify some coordinate system. And this singular field at second order, sometimes it's a bit unruly. So it would be nice if this whole philosophy could be formalized and it could be explained from first principles to any order in perturbation theory. So as a starting point, there is a nice way to derive this at first order, which is called Detweiler-Whiting. And they invented at first order a very neat way to regularize the field that goes something like this. First, you naively solve the Einstein equations and you get the retarded metric perturbation. So here, plus means retarded, minus means advanced, and this G is the Green's function that solves the linearized Einstein equations. Z is the path of the particle, and U is its force velocity. So this is just the solution to the linearized Einstein equations. But then they find a way to construct a singular Green's function that needs to satisfy some special properties that they will discuss later. But the important thing is that they realized that they could construct a retarded regularized Green's function by subtracting from the retarded Green's function its singular piece. The problem, of course, is that they only did this at first order and no one had any idea how to continue it to second order. So this Green's function approach was a bit abandoned. And this is the goal of this work, is to try to generalize this. So first question is there a way to derive this singular two-point function and all its properties from first principles, from physical, well-motivated principles? Second, can we extend this idea to any order in perturbation theory? And at the center of this project is the question, is it true that self-gravitating objects always end up moving as test objects in some effective metric? So is it true that you can always take out the self field and reabsorb it into some redefinition of things so that the objects end up moving on geodesics of some effective geometry? So that's what I'm going to talk about. So first, let's set up the model. I'm going to use a scalar toy model just because I don't like indices, but everything works in the same way for gravity. And the main idea is that we are going to start with an extended object. So here we have an action principle for phi, the scalar field, and some matter degrees of freedom that are coupling to the scalar field via the last term. The scalar field has some self-interacting potential V so that it reproduces the nonlinearities of GR. And the idea is to start with an extended object because everything is finite when you have an extended object, because the 1 over R divergences are not divergences because you don't get to R is equal to 0 because the object has some extent. For the high energy people, the length of the object is a UV cutoff for the UV divergences. At that level, we are going to regularize everything. We're going to take out the self field and absorb it into some renormalization of other variables. And then we're going to take the point particle unit. That's the spirit of what we're going to do. So we have this action principle. These are the equations of motion. An important thing I want to emphasize, equation 11a is derived simply from two facts. The action has to be diffeomorphism invariant or coordinate transformation invariant, and then the equation follows from the Nether's theorem. And the action needs to be separable into a piece that only depends on the field and a piece that depends on the field and the matter degrees of freedom. And that is enough to get equation 11a. So the main idea, if you have to take anything from it, is that we want to define a mapping from phi, rho, and t to new versions of those variables with hats, such that the equations of motion for the matter are the same. So if you look at equation 12a, it's the same as equation 11a with hats. So the form of the equations is preserved, but the field phi hat is now homogeneous. It's not sourced by rho anymore. If you compare equation 12b to equation 11b here, the rho term on the right-hand side is gone. So in this way, we get rid of the UV divergences of the field. The field is not sourced by the particle anymore. There is no 1 over r potential. So when we take the point particle limit in the end, phi hat is going to be regular and stay finite and well-defined, even in the point particle limit. And we will also want to impose of this mapping certain causality and locality conditions that I will explain in a bit, because we don't want this phi hat to be some crazy non-causal object. We want it to remain more or less physical. Okay, so how do we do this? The first idea goes something like this. I mentioned that if the action is split in this way, so there's a piece that depends on the field and a piece that depends on the field and the matter degrees of freedom, and if it's diffeomorphism invariant, then we get the form of the equations of motion. Now, this splitting is a bit arbitrary. We could add and subtract some function and it would still be okay, unless this function depends on phi and rho, because then it would mess up with the property that the first term should only depend on phi. So here's the idea. Let's add and subtract some function that depends on phi and rho, and then let's find some new coordinates in which the first term only depends on phi hat. So even if the first term depends on phi and rho, because its W depends on rho, let's find some new coordinates, phi hat and rho hat, such that in the new coordinates, the first term still only depends in the new field phi hat. By doing that silly trick, we get a canonical transformation. This W acts as a generating functional, and the equations that relate old variables to new variables are that of a canonical transformation. You see that this W hat that I introduced in the action is some identity plus a generating functional that in this case is type 2 because it depends on one old variable and one new variable, if people remember Hamiltonian dynamics. And the equations that relate the variables are the derivative of W with respect to rho gives you phi, and the derivative with respect to phi hat give you rho hat. So we have discovered a very general mapping. Basically, you give me any generating functional W, and that produces a mapping that already reproduces this form of the equations of motion. So that's one point that we already satisfied. But now we want to impose more conditions on W so we can constrain it enough so we can actually calculate what it is. We also want the mapping to be such that the new field phi hat is homogeneous. That means that this W is going to have to satisfy some field equations. We also want this new phi hat to depend causally on rho hat. That is, if the original field was a retarded solution, then the new field should also be retarded. It should not start depending on rho hat in the future or spatially separated. It should remain causal. So this is going to be some equation, like equation 17, where the derivative of the field with respect to rho vanishes when x and y are suitably separated in a way that I will explain in a moment. Also, rho hat needs to keep compact support close to rho. That is, if the original system was some neutron star or some compact object, then rho was compact. When we do the mapping to rho hat cannot suddenly become extended all the way to infinity. It needs to be more or less as compact as rho. And this will mean that rho hat will have to vanish for points that are far, quote unquote, from rho in some way that I will also define in a moment. So let's go over these three conditions. First of all, this is important. Everything I said so far is non-perturbative. This W non-perturbatively modifies the action and non-perturbatively maps the equations and the variables to new variables. Of course, doing things non-perturbatively is very hard. So now we are going to expand this generating functional in powers of rho. So the first term is just an identity term. So if you had only the first term, this mapping would be the identity mapping. And then all the other terms are n integrals of n-point functions times n factors of rho. Importantly, these n-point functions are still functionals of the field. We're only expanding explicitly in powers of rho. So if you want to get an idea of the type of mapping this does, it looks like this. So under this mapping, phi hat becomes phi minus all these n-point functions, and rho hat becomes rho minus the functional derivatives of all these n-point functions. And if we were to take a very simple linear theory, it would look like this, like equation 20a and 20b, which is exactly the Dead-Weiler-Whiting regularization that self-force people knew how to do at first order. And all the conditions that I mentioned, that the new field needs to stay causal and local, and it has to be homogeneous, exactly give you the properties that Dead-Weiler and Whiting more or less guessed for the two-point function, for the singular Green's function. But now we have a formalism where we can keep this machinery going and calculate these singular endpoint functions to any order we want. And we can subtract them from the physical field to get an effective field that is homogeneous. And that means that then we can take a point particle limit and be safe and sure that the field is going to remain finite. So how do we impose conditions in these endpoint functions? Well, the first one is the homogeneity condition that I have talked about. How to get these equations is very simple. You take the field equations for phi, you replace phi by phi hat minus the endpoint functions, and then you demand that phi hat is homogeneous. And in return, you get a bunch of equations for each endpoint function. And that determines the field equations that the endpoint functions have to satisfy. I should mention that the endpoint functions must also be fully symmetric under exchange of arguments. And that is simply because they are coming from a generating functional, and the n integrals symmetrize the arguments of the endpoint functions. So they need to satisfy some field equations, they need to be fully symmetric. Also, subtracting the singular field shouldn't affect the causality of the new field. So if the old field was retarded, the new field needs to stay retarded. So that is done by demanding that the endpoint functions vanish for time-like separations. So G2 vanishes if the pair is time-like, meaning that if this is the world 2 and x1 is here, x2 can only be here, can only be spatially separated from x1. So when we take the point particle limit, this is going to collapse to coincidence, which is what we want because these are UV divergences that we are trying to fix. So they shouldn't affect the past of the particle. Similarly, for the 3-point function, it needs to vanish if at least two pairs are time-like. And for all the endpoint functions, we have causality conditions where we demand that they have to vanish if some amount of pairs is time-like, and this guarantees causality. The next and last condition is the locality condition. And this one, I hope I can explain it correctly. Recall that the effective mass rho hat is the old mass density minus the functional derivative of the endpoint functions. And the argument of rho hat appears here in the functional derivative. So the way to make rho hat have a similar compact support as rho is this. We are going to impose that the endpoint functions depend on the field only in the convex hull of the arguments of the endpoint function. What is the convex hull? The convex hull of a set of points is the smallest region containing the points, such that every point in the domain can be connected by a geodesic. So if you have 2 points, the convex hull of those 2 points is the geodesic connecting them. If you have 3 points, in flat spacetime, it will be a triangle, and in more complicated spacetimes, is going to be some shape, but it's always true that the convex hull of a set of points is intuitively the neighborhood of those points. So because all the arguments of the endpoint function are contracted with mass densities, these all lie in the world tube of the object. So this one is confined to the convex hull of the world tube. So compact, it's easy to prove that the convex hull of a compact region is a compact region. So rho hat stays compact. So with this, we have defined the mapping. These endpoint functions, we know how to calculate them, at least up to second order. I have backup slides for that, but it was a bit technical, and I thought that it would be better if I present some applications instead. But we know how to calculate them in order to obtain the effective description up to second order, at least. And we have the equations to keep going, but it gets more complicated, of course. So how do we apply this in practice to do anything useful? First of all, like I mentioned, the description in terms of these endpoint functions was a bit abstract because they were still functionals of the field. So in a sense, it was a very self-consistent description where we were solving for the field, but the endpoint functions also depended on the field. But in the end, we are going to be doing an expansion in powers of the mass of the secondary. And that means that we can expand the field phi in background plus corrections. If we were doing gravity, phi bar, the background will be the field of the primary, and then we would get corrections. So we will only ever need the endpoint functions evaluated in the background, which I call GS for singular, and first derivatives of the endpoint functions evaluated in the background, which I call n, 1, because there's one derivative. So recall that the original transformation looked like this, and this endpoint function depends on phi, and it's a bit messy. But in the end, what we want is simply phi hat as a function of rho hat. That's this object we want. That's the field sourced by the charge density. And you can imagine that here there's a rho instead of a rho hat, so you need to plug this rho into here. But then this also depends on phi, so we need to put phi on shell and find what the retarded solution is and put it in here. So there's a bunch of algebra, but in the end, phi hat as a function of rho hat looks like this, where phi hat is the background plus an effective or regularized retarded 2-point function plus a regularized 3-point function, where these two guys look like this. The explicit form is not super important. There's two things that are important. First, this equation is exactly the Detweiler-Whiting regularization scheme that people were already using in the cell force. And this new equation is the generalization to second order. And the only important thing is that in order for us to know what this is, we need this 2,1, which is the derivative of the 2-point function with respect to the field, and this G3, which is the 3-point function. And as I said, we know how to calculate these guys. So with this information, this is giving us an analytic expression for calculating the second order set force in terms of these endpoint functions. So now let me talk about extended objects and how to describe them. The formal way to describe an extended object in general relativity is to use a generalized momentum P. This is a function of chi, which is some vector field. And the idea is that you integrate the tensor, the stress energy tensor, against this field over some surface. Here, sigma S is a surface, and S is the label that is describing each foliation of spacetime. And the idea is that if this vector field is a killing vector field, so if it's a vector field describing a symmetry transformation, for example, if it represents time translations, then this is going to be the energy. And if this vector field describes spatial transformations, then this is linear momentum. And if it describes rotations, this is angular momentum, and so on. So this is a very compact, neat way to define and to describe all possible conserved quantities in terms of just one function. Now, by the equation the equations of motion of the matter degrees of freedom. So the gradient of the stress energy tensor is equal to rho times the gradient of phi. It's easy to change this equation into this equation. And you can see, so this L is the Lie derivative. And you can see that if this vector field is a symmetry of the scalar field and the metric, then these two terms vanish, and then the conserved quantity is actually conserved. But in general, these are going to be forces that take energy away from the conserved quantities. Now, this is the way to describe conserved quantities, or the evolution of conserved quantities for extended objects. But now that we have this mapping to effective variables, because the mapping preserves the form of the equations of motion for matter, we immediately get the same equation with hats. And the important thing is that this now describes the evolution of conserved quantities of objects that are strongly self-interacting. So this phi hat is the effective field that we got after taking out the self field and absorbing it into a renormalization of rho hat and t and the conserved quantities. But it doesn't have to be a test object. We are describing an object that can be arbitrarily strongly self-gravitating, like a neutron star or a black hole or whatever we want. From this equation, there's a couple of steps that are straightforward but a bit tedious. To get the MPD equations, these are Matheson, Papaperchuk-Dixon equations that describe extended objects in a multiple expansion. So this equation 24 describes the extended object in terms of rho, which is the full dynamics of the fluid or whatever it is. And we can get from 24 to 25 by doing a multiple expansion. And then we get an equation for P, that is the linear momentum, an equation for S, that is the spin tensor. This R is the Riemann tensor that describes the curvature. So this is the spin curvature coupling. And then this first term that I included is the monopole term. So it's just the total charge of the object couples to the effective field like so. But all the dotted dots in these equations are all the higher order multiples that we can easily derive from equation 24. And the important thing that I want to emphasize is that MPD, Matheson, Papaperchuk, and Dixon derived this equation for test objects. Because when you do a multiple expansion, you need the field to be slowly varying over the extension of the object, because otherwise the Taylor expansion required to expand in multiples just doesn't make any sense. When you have a strongly self-interacting object, it has a self field that actually varies rather quickly over the extension of the object because of the 1/r potential. So you cannot do a multiple expansion. But because we developed this way to map the field to an effective field that is an external field in the sense that it doesn't have divergences anymore at the location of the object, the multiple expansion is protected and it's fine, and we can take this point particle limit plus multiples and we can include consistently the self effects, basically. So this will be useful to study tidal effects of neutron stars or things like that if you want to consistently consider and not neglect its self field. So now I want to change topics a bit in the last minutes and talk about Hamiltonian dynamics. So of course, the two-body problem is dissipative. There's gravitational waves radiating away. But for most approximations, there's a sense in which the dynamics can be split into a piece that is conservative, so it doesn't radiate away, and it only modifies certain parameters of the orbit, and a piece that is purely dissipative and is responsible for radiating energy. And the way this works is that we generally have some zeroth order unperturbed system that is Hamiltonian, and we are adding a perturbation. So here, I think this equation needs some clarifying. This QA is just my compact way of calling the phase space variables. So this A index goes from position and momentum, for example. And this omega is the symplectic form, so dx wedge dp, and this h is the Hamiltonian, and this is the derivative respect to position and momentum. And if we add some perturbation to the Hamilton's equations, The question is, when can this be recasted as a Hamiltonian system? And the answer is fairly obvious, is if you can absorb this term into some extra terms in the symplectic form and some extra terms in the Hamiltonian, then this perturbation was actually Hamiltonian all along. You could recast the perturbed Hamilton equations as new, exactly Hamilton equations in some new Hamiltonian system. So why is this so hard to do in the cell force and in general in the two-body problem? The answer is because of tail terms. So the cell force, just at first order schematically, it looks like this. It's the cell force at position z is the gradient of the integral of some two-point function, where the gradient is acting on z, but the two-point function is sourced by the past history of the particle. And the idea why this looks like this is because along the trajectory of the particle, it's possible that the particle emitted some gravitational waves, and because spacetime is curved, these gravitational waves back reacted and scattered off and were reabsorbed at a later time. So for high energy people, this is like a Feynman loop, basically. It's like a graviton being emitted and reabsorbed. So it's like the self-energy of the particle. So this is why the cell force looks like this. And these tail terms appear at first order in the cell force, but eventually they appear in all approximations. They appear at fourth post-Newtonian order, I think at third post-Minkowskian order, might be a different order, but eventually they show up. And the problem is that this looks like it's the gradient of a potential, in which case it would be trivial to add it to the Hamiltonian, but it's actually the gradient of a potential that is secretly a functional of the path. So it's not a local function of the position, but it's a functional of the full past history of the particle. And we cannot simply add this to the Hamiltonian because the Hamiltonian should be a local function on phase space. It should depend on position and momentum now, not position and momentum now and everything the particle has ever done in the past. That's not a Hamiltonian. So this is the main obstacle with finding an actual Hamiltonian description in the two-body problems, tail terms, or memory effects, or however people want to call them. So let me explain very quickly how this is solved. Usually the unperturbed motion, which is Hamiltonian, can be described with an action principle. So this action principle gives you Hamilton's equations. In the case of the cell force, geodesic motion, so unperturbed motion, can be described in this way. And it's a neat, interesting fact that the first order dynamics, when you describe them with the two-point function, can be derived from a non-local action principle, where this first term is this guy, but there's a new term that has two time integrals. So it's non-local in the sense that it's integrating at different times. And you can see that when you vary this respect to z, there's going to be a variation of the first term, a variation of the second term. That's going to be a factor of 2. That is cancelled by this 1/2, and you recover the equations of the cell force. The important thing here is that because we are integrating 2 times, the integral is going to pick the symmetric piece of the two-point function. So you're not going to recover the full cell force that you started with. You're only going to recover its symmetric piece. That is exactly the conservative piece. So with this fact, I got inspired a year and a half ago. I wrote this paper that is just a simple proof in Hamiltonian dynamics, which goes something like this. If you have an action principle that has some zeroth order piece that is only one integral over time, so it's a normal action principle, and then you have as many corrections as you want that are n integrals of n-point functions evaluated on phase space paths that are perturbative in some sense. So there's some small parameter that accompanies each term. If you have an action that looks like this, then there is a local Hamiltonian description. You can go to the paper and check. It's an annoying, tedious proof, but it's done. And I find the equations and the formulas for a local Hamiltonian and a local symplectic form that describe the dynamics of the systems. And the only condition is that the endpoint functions need to be fully symmetric. So this was actually the motivation for everything I said before, because we had to find a way to describe the self-force in terms of endpoint functions that were regular and well-defined in order to apply this proof. Because it was not obvious that the self-force beyond linear order, beyond first order, that it could still be described by endpoint functions. But by the field redefinition that we developed, it can be described by endpoint functions, and then this proof applies. So we find a local Hamiltonian description for the conservative sector of the second order in dynamics. And the prescription for finding the conservative sector is simply this. You take the retarded endpoint functions that describe the full dynamics, and you symmetrize them under exchange of arguments. So with this, let me give you some takeaways and future directions of the work. The takeaways are not too many. It's very simple. We proved that there is a field redefinition so that self-gravitating objects move as test objects in an effective external field to any order in perturbation theory, given that the endpoint functions exist, which we have shown that they exist up to second order, at least. And with these endpoint functions, we can write the second order self-force in an analytical way, which is useful because we have analytical formulas. And the dynamics arising from these endpoint functions can be cast as a local Hamiltonian system. And having a Hamiltonian is very useful because there's other approximations that also calculate Hamiltonians, and then we can compare Hamiltonians with the post-Newtonian or the post-Minkowskian approximations. And also the Hamiltonian machinery is very useful to have at our disposal. As future directions, I should mention that another important aspect of Hamiltonians is that the effective one-body formalism, the EOB approach to two-body dynamics, requires a Hamiltonian as an input. So this is an interesting avenue for informing EOB with self-force. Also, these singular endpoint functions can be very easily expanded in a post-Minkowskian theory, so starting in flat spacetime and then adding corrections, and that allows for comparisons with PM as well. Also, once we have this effective action principle, there's a lot of gauge invariant observables that become available to study the two-body problem, and gauge invariant quantities are also are always important because they remain the same in all approximations. So they're a really nice benchmark to compare different methods. And there's one tiny thing that I hid until now that I should mention, which is that when you're dealing with conservative dynamics, there are infrared divergences. And we so far don't know how to fix that. So the field redefinition works perfectly fine, and the Hamiltonian proof works fine. But if you're going up to second order and you're using a bound orbit, there are some infrared divergences. And the reason is not too complicated, is that if you have a conservative bound system, it's orbiting forever and it's emitting an infinite amount of energy. And when you go to second order, there's an infinite density of energy in the space-time. So it produces infrared divergences. And that is something that we're trying to fix in the near future. And with that, I will take any questions. Thank you so much.
Thank you, Francisco. I think there is a delay, so if we get a question on YouTube, I'll read it to you. Thank you for this very nice talk. I'll start with maybe two ill-posed questions for sure, so bear with me. So the first one is, can you again clarify the connection of what you study for the extended body for, let's say, the gravitational problem? I think I missed the connection because you are here assuming there is a scalar field on a static background. So maybe that's the part I actually lose the connection.
So
just
everything I explained uses a scalar toy model.
Right.
So you have some static metric background, and then there's some primary object that has some scalar charge and a secondary that has some scalar charge. You replace gravity with scalar charges. It's just an easier toy model, but you can replace the scalar with gravity and it works exactly in the same way. It's just a simpler toy model just to show equations, and everything looks a bit more intuitive to explain. But it's the scalar self-force, basically. Is instead of the object interacting with its own gravitational field, it's interacting with its own scalar field.
Yes. Okay. And then,
Um,
but then the space-time is static, right? So how do you, or like how is like the, let's say, the dynamics? And also how important is that you have this scalar being non-linear, because the non-linearity that you can add can be very different from, let's say, the one that you will get if you were to solve the full GR problem, right? So
yeah,
is it clear that you can capture like the full gravitational problem in this language and then
well, the
non-linearities
toy
of
model,
GR?
the toy model is just a very naive attempt to
Yeah.
have a very simple nonlinear model to do all the equations. It's not obvious that
Yeah.
this should also work from gravity, but it does.
Okay.
We can write this field definition. So in this starting point,
Yeah.
instead of having this scalar, we just have the Hilbert action, the Hilbert-Einstein action, and instead of having this coupling, we just have the matter Lagrangian that automatically couples to the metric by virtue of being on a curved background.
Mhm.
And then the equations, instead of looking like this term is zero because the matter is going to move on a curved spacetime. And then the field definition takes you exactly to the same equations without this. And these are just the vacuum Einstein equations instead of being sourced.
Okay.
But the whole formalism works in the same way. Um,
Okay.
yeah.
Thank you for the clarification. And the other question is related to the last part that you were mentioning, the conservative sector, and then how can you capture this as a Hamiltonian?
Yes.
So just again, if you can repeat the connection. So if you have a body that, or yeah, then you have, let's say, the two-body problem, or in general, you have a system that is Hamiltonian, and then you perturb it.
Yes.
The perturbation can be anything. So it could be non-integrable, it could be integrable. So how does this relate to that? In the sense that you can always, like your results are, you can always capture the conservative part as a Hamiltonian like that. But then do you need any, or I guess my question is also to the requirement that I think you need this 2-point function to be symmetric. Is that
Yeah.
related to some property of the specific perturbation, or it can be any general perturbation that is non-integrable will satisfy that?
That's a great question. So the proof I showed is specific to perturbations that look like this. So the perturbations need to be um,
Yeah,
integrals of endpoint functions over the history of the particle. When the forces look like that, which is a very specific for, it's
yeah,
not like any perturbation. They have to
yeah.
be an endpoint function, but it is the form that every perturbation in the two-way problem takes, because it's always the effect of gravity in the past being absorbed in the present, and it always looks like that. Whenever it looks like this, the conservative sector is the symmetric piece under
Yeah.
exchange of arguments of the
Okay.
endpoint function. And that is the piece that allows you to build a Hamiltonian.
Yes. Okay.
And then everything that's left is the dissipative sector, basically.
And okay, I said two questions, but okay, but as I said, this is fascinating. But then just maybe I don't know if there's another question, and while someone raises their hand or I check something on the YouTube, I would like to ask you again: is there a way like to then somehow reconstruct a metric? So if you can have that Hamiltonian, or you do that, can you give like the reconstruct the perturbed metric of whatever it was?
Absolutely.
Okay.
Yes. So these endpoint functions are, so basically, if we go back to maybe this slide or this slide, no, this slide, no, which one is it? There you go, here. Uh, here. So
I see. Sorry. Okay, I missed it.
this big object,
Yeah.
if you like write the whole integrand as a 2-point function
Yeah.
scalar without any indices because everything is already like contracted. It depends on position, and then it's integrating the phase space path in the past. Depends on some position and velocity that is integrated in the past. And that object is exactly what ends up changing the metric. So it is exactly true that in the end, the secondary moves on a geodesic of
Yeah.
an effective metric. That is
Okay.
the background plus all these endpoint functions that give you the corrections to the metric that are basically this red thing,
Mm-hmm.
minus the divergent piece, is the regular part of this red thing.
And then, okay, sorry. And more questions from here. Anyone here in the chat has a question? I don't see. Let me check. I also don't see questions on YouTube. Okay, I see someone. Yeah, Roberto, go ahead.
Yes, I have a question for Francisco. So I mean I'm not from the field, let's say, but the
From the
infrared
effective field.
radiation from the field, yeah. I'm outside the field now. Now I'm saying the infrared divergence that you have is because of the point-like sources, or I mean because
No.
I mean let's say the green function is already like 1/r in the assuming that it's kind of
Yes.
Newtonian, or could be no matter it's always there.
It's unrelated. Maybe I have some backup slides to explain this. Do I have that? So many backup slides. Here it is. Okay. So when you have a retarded Green's function, you have the binary system and it emits some waves to infinity. When you have an advanced Green's function, it receives some radiation and then it keeps going. Because the conserved Green's function, the conservative Green's function is the symmetrization, is the retarded plus advanced Green's function. And that produces a standing wave to infinity. The system, because it's conserved, it needs to receive every bit of radiation that it emits at the exact same rate, so it stays bound but not in spiraling forever. At first order, that's fine. It's a bit weird. You have infinite energy far away, but your system is still well defined. But at second order, the first order field comes back as a source. So then you have infinite energy in your spacetime, and that comes back as an infinite source, and everything just blows up. So the problem is specific to the conservative sector and specific to bound orbits, because if you have a scattering event, the radiation happens for a bit, and then for a small window of time, and then it goes away. So the only situation where these infrared divergences arise is if you're studying conservative dynamics of bound systems to second order. Any other thing, it's fine.
Great.
Okay,
Thank
I understand the difference between the typical case in quantum field theory or field theory in general.
It's not because of the 1/r. No, it's something else. Yeah.
Yeah.
Good.
Cool. Thanks.
Okay, I think like we have one extra minute. If there's any question, I don't see anything on YouTube. Okay, wonderful. Okay, well, thank you, Francisco, for being part of this low physics webinar. As I said, like the recording will stay there forever, so people might be able to still contact you. For the rest of the audience, stay tuned for the next low physics webinars happening in 2 weeks. And Francisco, once again, thank you very much.
Thank you. It's a pleasure.
Okay, let me just finish this and I think we are not live. Okay, we have 25 views on YouTube.